Hi, these are the section 1-3 notes. The section title is called Transformations of Function Graphs. And I'm going to apologize in advance for my penmanship. You see me write on the board. It's not great. Me writing on a tablet is even worse. You should hopefully remember from your geometry class there are 4 primary types of transformations. So the first kind you probably talked about was a translation. So maybe I have this triangle. This would be my pre-image. And for a translation, we're just going to pick up the image, and maybe we move it over so much and up somewhere else. Oops. And you're going to have the exact same shape, just in a new location, right? That's not what I wanted to erase. That's good enough. Okay, so that's a translation. Oh, and this would then be the image, right? I believe was the terminology we used. The next kind is a dilation. So for a dilation, what you did is you started with your pre-image, and then that pre-image, depending on where you centered your dilation, might have expanded it. So you're keeping the same proportions. Or you could also do a dilation that contracts it. So it's a pretty lousy looking triangle, but you can pretend that it's the same proportion triangle, and that it's a triangle at all and not some shaky piece of junk. The third kind, black. The third kind was reflection. So to do a reflection, what we said is there's some plane that we're going to reflect across, and you're going to get a mirror image of it. So something that looks like that. So it's the same shape, it's just been reflected across that line. And the fourth kind you talked about was a rotation. And this is something so we typically don't worry about rotations in a high school math class, at least a rotation of a function. If you took, a college linear algebra course or something, you'd probably talk about this, but beyond the scope of this course, so we're not going to talk about these. So up until this point, when I talked about translations, dilations, and reflections, I did them in terms of geometry, in terms of a geometric shape. We can also think about these in terms of functions, or a graph of a function. So for some function, f of x, the transformation of that function can be written as g of x equals a times f of 1 over b x minus h plus k, where if a is greater than, less than 0, there's a reflection across the x-axis. If b is less than 0, we have a reflection across the y-axis. If the magnitude of A is bigger than 1, so these vertical bars are the absolute value bars. So when I say magnitude, it's like the same thing as an absolute value. That gives us a vertical stretch. And when the magnitude of A is less than 1, that's a vertical shrink. So just to be clear, when I say magnitude of A greater than 1, so for example, if A is positive 2, that's greater than 1. Or if we talk about if A is negative 2, the magnitude of negative 2 is also positive 2, so that's also greater than 1. Similarly, the magnitude of negative 1/2 is 1/2, that's less than 1. Or the magnitude of positive 1/2 is 1/2, and that's also less than 1. So basically, these vertical shrinks are things between -1 and +1, and these vertical stretches are the things bigger than +1 or less than -1. If the b value is greater than 1, we'll have a horizontal stretch. The magnitude of b, and so magnitude of b is greater than 1. The magnitude of b is less than 1, we'll have a horizontal shrink. If h is greater than 1, we're going to translate right h units. And again, I wrote absolute value here because if h is negative, like in this case, it'll go left absolute value of h units. So like, I just put the absolute values there because the sign really tells you the direction. So I wouldn't want, if h is -5, I wouldn't want to say left -5 units. That doesn't make sense. We're going left just 5 units. So the direction on the x-axis is already kind of dictated in there. So if the k is positive, we're going to go up k units. And if the k is negative, we're going to go down k units. So this information here is really important. So this is something that you're going to want to memorize. You're going to want to know the general form of a transformation. And then you're also going to want to know what the constants, the a, b, h, and k, do to a transformation. So that's going to be really, really important. We're going to use that a lot in this section, and we're going to use that a lot in future sections, and you'll use this a lot in future courses. So like your trigonometry course next year, if you take that, you'll also be using these same set of criteria. So this is something you really want to memorize, and you don't want to memorize it just for a day. This is something you want to memorize for, like, forever memorize. Okay? So let's do some examples of using this. So let's say that we want to, let's say, write the transformation of f of x that is, well, maybe we should say just that, translates f of x 5 units to the left and reflects across the y-axis. So to do this, I'm going to go back to my set of criteria. I know that this translation that I'm going to write is going to be in this general form. I just need to determine what the values of a, b, h, and k are from the descriptions going here. So I'll go back to my criteria, and I'm going left 5 units. So that tells me the h value should be -5. Okay? So I'll go ahead and fill in -5 for h. The next thing it says is it reflects across the y-axis. So I'll go and figure out which one does that. So that tells me b-values that are less than 0. So I know the b-value is going to be negative, but I don't have any information about a horizontal stretch or a horizontal shrink here. So there's only one number that is not greater than absolute value of b or less than the absolute, or I'm sorry, there's only one number where the absolute value of b is greater than 1. I'm sorry, let me try this again. There's only one number where the absolute value of b is not greater than 1. And also, the absolute value of b is not less than 1. That number is specifically 1. So, that tells me that the b value is -1. Okay. And minus a -5, well, minus a negative is positive. So I figured out the b, and I figured out the h. Now I need to determine the a and the k. Well, let's look. I don't have a reflection across the x-axis, so that tells me the a is positive. And because there's no vertical stretch, and there's no vertical shrink, I know that it's not greater, a is not greater than 1, and a is not less than 1. So that tells me a is specifically +1. Okay. And 1 over -1 is just -1, and since it's in, oops, there we go. And now I'll do the k. So there is no translation up or down, that's what the k does. So since I need the number where k is not greater than 0 and k is not less than 0. Well, that happens specifically only when k equals 0. So I know that k is 0. So here's my final answer. I could write this as, well, 1 times anything, that doesn't change anything. And multiplying -1 into a parentheses is the same thing as just writing a negative sign outside the parentheses. And anything plus 0 is itself. So that tells me this is my translation for this description. In the assignment, you might also be asked to, they might also give you a graph for f of x. So maybe we have, this is our graph of f of x. Maybe this is the point 0, 0 here. And it's going to ask you to go down 5 units. So, to do that, I'm going to just draw this on the same axis. I'm just basically taking everything and moving it down. So this point now, instead of 0, 0, is at 0, -5, and then I'm just kind of sketching the rest of it. So I, again, literally just picked the graph up and moved it down 5 units. So you might have to do something like that in the assignment. Another thing you might have to do in the assignment is we might have to take a translation. So say that g of x is -3 times f of 2 times quantity x plus 1 plus 7 is a translation of f of x. Write a description of that transformation. So this is not too bad. What you'd want to do is you'd want to start by identifying the values for A, the values for B, and let's actually do this, the value for H, and the value for K. So to do that, I'm going to go back to this information that I wrote up here that I said was very important that you should have to memorize. So I know that the a value is this part outside the f. B is that coefficient inside the x. H is that thing that's being subtracted from the x. And k is the thing that's added to the end. So I'm just going to, before I get going, just copy that down. And I guess I'll just so I don't have to keep scrolling up there all the time. So if I look at this, it's easy to see, well, the a value, that should be -3. 1 over b is 2. So if I think about that, if 1 over b equals 2, I can cross multiply. And if I divide by 2, I get 1/2. So b is 1/2. If you don't like doing that, you can just remember the rule that this number, the b value is the reciprocal of this number. So you can think about it that way too. The reciprocal of 2 over 1 is 1/2. Either way of thinking about it is fine. The h value, now a lot of students would say the h value is +1. Unfortunately, that's incorrect, because if we look at the general form here, it needs to be written as x minus h. So I know that minus a negative is the same as addition, so what I really have is x minus a -1. So h is -1. Again, if you don't feel comfortable with that, just remember the fact that the h value is always the opposite of the sign that's written here. And the k value is just 7. Okay, so I've done that. That wasn't too hard. Again, all it was reading it basically from the function based on this general form. What I'll do next then is go up to my list of criteria, the piece that I asked you to memorize, and use that to determine what's going on. So, scroll back up. Well, my a value is -3, so it's less than 0. So I definitely have a reflection across the x-axis. Let's go write that down. But the a value, I remember, could do more than one thing. If I scroll back up, my a value is -3. Well, that means the absolute value of -3 is also greater than 1, so I also get a vertical stretch. Okay. Now I'll go to the b, and I'll scroll back up. My b value is 1/2. Well, that's not less than 0, so there is no reflection. But the absolute value of 1/2 is less than 1. So I do have a horizontal shrink. So that's the only thing I'll write. If there's no reflection, I don't need to write anything. And now I'll go look at my h. So my h is -1. Well, -1 is less than 0, so I must be going left 1 unit. And my k value is 7. So 7 is greater than 0, so I must be going up 7 units. And there's that. So you might also be asked to do something like this. The last topic that we need to worry about, there is 2 more topics that we need to worry about. So I'm going to put like a hard line through here because this is not directly related to what we are doing. So I'm going to define a few terms. So we're going to define the term odd and even. A function is odd if f of -x equals -f of x. And we say a function is even if f of -x equals f of x. So let's just look at a couple of examples of things that are odd and even, and then we'll talk about how to show something as odd or even. So f of x equals x squared is even. F of x equals x cubed is odd. And f of x equals x squared plus x cubed is neither. So let's show how you would figure that out, because I'm just claiming this. I mean, I could say the wrong thing, I could say the right thing, you don't know. You should say, any good math student would say, yeah, okay, so can you prove that? And I would say, sure, we can prove this. So to prove this, to show, say, x squared is even, what I need to do is show this relationship. Okay, well, that's not so bad. So if I want to prove two things are equal, I'm going to start on the left-hand side. So I'm going to write f of negative x. So remember, just as an aside, and maybe I should write that in a different color. If I have f of x equals 2x plus 5, and I do f of 2, that tells me to just plug 2 in for the x's. So if I have f of negative x, what that's telling me is to plug negative x in for the x's. So I'm just using my definition of what f of x is. Okay. And now let's simplify negative x squared. Well, I know that 2 squared is 2 times 2, so negative x squared is negative x times negative x. And I remember that negative times negative is positive, and x times x is x squared. And if I go back and I look, what is x squared the same as? F of x. So to use another geometry term, what I've done is I've shown f of x, or f of negative x, is equal to f of x using transitivity. So you remember transitivity from geometry, that if a equals b and b equals c, then a equals c. So we've just linked this stuff all together through equal signs. So this is equal to this, and this is equal to this, and this is equal to this, and this is equal to this. Then the ends must be equal, because they're just linked together through a bunch of equal things. Okay, so let's do the next one. Oops, that's not what I asked for, computer. So now let's show that f of x equals x cubed is odd. So again, just like before, if I do f of negative x, I need to substitute the negative x in for x. And just like 2 squared was 2 times 2, 2 to the third is 2 times 2 times 2. So negative x cubed is going to be negative x times negative x times negative x. And I remember that negative times negative times negative is negative. And x times x times x will be x cubed. So in this particular problem, we're told that f of x is equal to x cubed. So negative x cubed must be negative f of x. And so what we've shown is that f of negative x equals negative f of x. So we know that this is odd. Great! We're almost done proving all of these things. Who knew proofs would be this quick and this simple? I bet you still disagree that they're quick or simple. To show something is neither, what I need to show is that f of negative x doesn't equal f of x, and it doesn't equal negative f of x. So I'm going to do the same thing. I'm going to start the same way. So I'm going to begin by taking my f of x and plugging negative x into both x locations. And now I'm going to cheat a little bit. I know what negative x squared is. That's just x squared. I did it in the previous problem. And I know what negative x cubed is. It's negative x cubed, because I did it in this previous problem. And now I'm going to look. X squared plus negative x cubed, well, that's not f of x. F of x is x squared plus positive x cubed. So I know that this does not equal f of x. And so I can say then it's not even. Furthermore, I know that negative f of x is going to be negative x squared plus x cubed, which is negative x squared minus x cubed. And positive x squared minus x cubed is not equal to negative x squared minus x cubed. Right? This x squared is positive, this one is negative, so they can't be equal either. So I know that f of x is not equal to negative f of x. So I have not, this function is not odd either. So what can I say? It is neither even nor odd. So to show something is neither, you just show that it can't be even, and you show that it cannot be odd. The last topic, kind of wholly unrelated to what we did there. Well, I guess as an aside, why are we talking about odd and even here? Because odd and even are technically reflections. I don't want to go into it, but that's why it comes up in this section, is because we can think about this as a reflection across the y-axis that is the same thing as a reflection across the x-axis. And this is a reflection across the y-axis is the same as not doing anything. So that's why it comes up in that section. You might have been asking yourself, what the heck does this odd or even thing have to do with transformations? And that's what. So the last topic here to talk about is modeling with a quadratic function. So before we get moving here, I'm going to define a couple of things. We're going to define something called a family of functions. And a family of functions is the set of all functions that can be written as, let's say, a transformation of the parent function. Well, that's nice, but what the heck is a parent function? Well, funny you ask, because that's the next thing I'm going to do. So a parent function is the simplest version of a function. Okay? So example, the set of all quadratic functions forms a family of functions where f of x equals x squared is the parent function. So we won't prove that or anything. You're just going to take that at my word. I know that's poor mathematics, but, well, you're just going to have to deal with it. So what I'm going to do now is make a claim. So we said that in general, a transformation of f of x can be written as g of x equals a times f of 1 over b x minus h plus k. And that's nice, right? It turns out for quadratic functions, we can write g of x equals a times f of x minus h plus k, where I can ignore the 1 over b value, and since f of x is x squared, we can take any quadratic function and write it in this form. So this is something that's important. You're going to want to remember this, that any quadratic function can be written in this form. And again, I'm not going to show you why that is. You're just going to have to take it as fact from me. So what we're going to do now is we're going to look at an example from the textbook. So rather than me trying to draw this in, since I have the option, I can just display the actual section from the textbook. And you guys are saved from me having to do just some really dreadful drawing on my part. Okay. Just do that, and that, and one of these, and actually, I will just do this. Okay, come on, come on, come on, come on. And move that there. And that's going to give me everything I need. Okay, so what I'm looking at here is example 2 from page 38 in your textbook. It says, an old stone bridge over a river uses a parabolic arch for support. So the parabolic arch for support, parabola is just the name of the graph of a quadratic function. So it tells me that we're making a quadratic function here. And since it's a quadratic function, that tells me that the form I'm going to write it in is this. Okay? It says in the illustration shown, the unit of measurement for both axes is feet, and the vertex of the arch is point C. Okay, so it tells me the vertex is this point, 27, -5. That's really convenient because it turns out the vertex of a quadratic and the h and k values are directly related. So it turns out the h is the x-coordinate of the vertex. So in place of h, I'm going to write the x-coordinate of the vertex, which is 27. And the k is the y-coordinate of the vertex. So in place of the y, in place of the k, I'm going to write the y-coordinate of the vertex, which is -5. I'm almost done. So the only thing I need to do to write my quadratic equation is figure out this a value. It says then find the quadratic function that models the arch and state the function's domain. So to find this other a, what do I have here? So I have an equation with 3 variables. I have a y-coordinate, this a coefficient, and an x-coordinate. So if I can find some other point on my function, some other xy that's not the vertex, I can plug that in for the x and y here and use it to solve for a. So if I look at my function, I'm given 2 such points. I'm given the point a here and the point b here. Now, not going to matter which one I use. I'll get the same value regardless of which one I use. I'm going to choose to use this one. So I'm going to plug the y coordinate in as my g of x. I'm going to plug the x coordinate in for the x. And now I'm at a place where I can solve for a. So I will just solve like I would in my regular algebra class. I'll add 5 to both sides. If I simplify this, 2 minus 27 is negative 25, and negative 25 squared is 625. And then I can just divide both sides by 625. And when I reduce that fraction, I get that a is negative 3 over 125. So I can say my final answer then is g of x equals a times x minus h squared plus k. So there's my model. Not so hard. So again, what did I do here? I took my general form for a quadratic. I used the vertex to plug in my h value and my k value. And then I used some additional point to find my a value. And then I just rewrote the whole thing. Okay. And then the question asks also to state the domain for that function. So the domain is just talking about the x coordinates. So I look at my picture here and I notice that it's all connected all the way through. So the smallest x coordinate is 2. And the biggest x coordinate is 52. So I'm going to write this as an interval using interval notation. And if I look at the x coordinate 2, that actually corresponds to some point. So that value 2 is used. So I'm going to use a bracket to show that it's included. And the 52 is used. So I'm going to use a bracket there to show that it's included. The last thing, I know I said that this was going to be the last thing like 3 separate times, and I keep on going. This is honestly now the last thing. Say I have some function. This is backtracking a little bit. So I really meant to put this, where did I mean to put this? Probably right here before I started talking about odds and evens. So I really meant for this to go here. I apologize. But I think it'll be okay. So this is the back in time. Meant to be talking about it there. Okay. Let's say we have a function. And this is not the color I picked. I have some function, f of x. And I've defined this function as this set of ordered pairs. And I ask you to graph the transformation of that function described as So it turns out that this is not that bad. The tool that I'm going to use to do this is the following. What I'm basically going to do is I'm going to make a map that's going to go between the x coordinates of f of x and then the xy, the points in f of x and to the points in g of x. So this, super important, this map where we can use it to transform my image into a pre-image. This is super important. This is something you want to memorize. I can use this now to transform my points from f, 1, -1, 0, 0, and 1, 1, into points from g, so that I can just plot those points and be finished. So all I really need to do is take my a, b, h, and k from g of x and plug them into this formula. Oops. Let's go back to black. So remember, the b value is the reciprocal of what's written here. The h is the opposite of what's written here. The a value is there, and the k value is there. So I'm just now going to plug in my values from f and just plug them into this formula. So I have 1/2 times 1 minus 1, and then -3 times -1 minus 6. So 1/2 times 1 is 1/2, minus 1 is -1/2, and then -3 times -1 is +3, minus 6 is -3, and then I have 1/2 times 0 minus 1, -3 times 0 minus 6. So that is -1, and that is -6. And then the last one is 1/2 times 1 minus 1, and then -3 times 1 minus 6. So when I do that, I have, oh my goodness here, goodness gracious, goodness gracious. This is a mistake. My apologies. I meant to write this as -1. Oh my dear, goodness gracious. Hey. And what is the reason why I knew that was a mistake? If I go back and look, I had a function with 2x coordinates the same. Well, that's not a function. Gee golly willikers. So, my apologies on that. Ooh, at least I caught it, though. Better late than never. Okay, so there's that. So, if I compare this, let's say I graphed f of x. So I had this, 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 and then I drew the other ones. And then 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have -1.5, -9, so maybe there. I have -1, -6. So that's here. And then I have -1/2, -9. That's there. So if I look at what's happened, I notice I've translated left and down. I've reflected across the x-axis because this was opening up and this is now opening down, and it looks a little bit thinner. So I've either I've done some kind of translation, or I'm sorry, dilation, where I've stretched this thing vertically or compressed it horizontally, or maybe some of both. So the advantage here of doing it this way is that I noticed that there was at least 4 or 5 transformations going on here because of the values of a, b, h, and k. I did it all as one transformation using this map, so I could go directly to plotting points. So that's it for section 1.3. So the big takeaways are remembering our criteria for transformation. So you need to remember the general form of a transformation, and then what the coefficients, the a, b, h, and k, do. And then you'll want to remember the general form for a quadratic equation. This is super important. And the general form for the map for a transformation if you wanted to graph it. And that will close section 1.3. Thanks, guys.